Welcome to the session on hypothesis testing with the normal distribution. The objectives for this session are to carry out hypothesis tests for the mean of a normal distribution and solve real-life problems in context. If we take many different random samples of size n from the population, their means would be normally distributed. For a random sample of size n, taken from a random variable x distributed normally with mean mu and variance sigma squared, the sample mean x bar is also normally distributed with x bar distributed normally with mean mu and variance sigma squared over n. We can use the distribution of the sample mean to decide whether the mean for a particular sample, x bar, is statistically significant. So let's take a look at an example. The times taken for a specified dose of anesthetic to take effect on rabbits are normally distributed with a mean of 183 seconds and a standard deviation of 15 seconds. The manufacturers of the anesthetic claim to have developed a new formula which will shorten the time for the anesthetic to take effect. A random sample of 25 doses of the new formula are tested, and the mean time for the sample is 177.5 seconds. Test at the 5% level whether or not there is evidence to support the manufacturer's claim. So let's solve this. We're going to begin by highlighting the key phrases in this example. Notice that we've highlighted normally distributed. We've also highlighted the mean, which is 183. We've also highlighted standard deviation, which is 15. And then we've highlighted shorten the time. So this is what we're going to test. Has the time shortened or has it not? We've highlighted the sample size, which is n equals 25, and the new mean time, which we're going to test, 177.5 seconds. And finally, we've highlighted the level at which we're testing at, namely 5%. So let's begin to solve this. Let's write out the hypotheses. H0, mu equals 183, and H1, mu less than 183. Has the time shortened or not? So this is the mean of our distribution, 183, and it has a standard deviation of 15. And we're going to test whether the time has shortened or not. Is this in the lower 5% tail, this particular value, this new 177.5 seconds? Is this in the lower tail or is it not in the lower tail? So let's set up the test further. We're going to let x represent the time taken for the anesthetic to take effect. And we're going to assume H0 or H0 so that x is distributed normally with mean 183 and standard deviation 15. So now we're going to write the distribution of the sample means for the sample of size 25. We have x bar distributed normally with mean 183 and variance 15 squared divided by 25. This is the same as x bar is distributed normally with mean 183 and variance 3 squared. Using our calculator, we can input x bar equals 177.5. We can input the mean equal to 183 and standard deviation equal to 3 in order to find the probability, which is equal to 0.03338. Now we can test at the 5% level whether or not there is evidence to support the manufacturer's claim. Now, since P equals 0.03338, and since this is less than 0.05, in other words, the 5% level, we can conclude that the result is significant, and therefore we reject H0. And therefore there is evidence that the new formula is an improvement. Now let's take a look at another example. Pause the video and have a go. Press play when you're ready to view the solutions. So let's take a look at part A first. The weights of grey squirrels in England are found to be normally distributed with a mean of 550 grams and a standard deviation of 33.3 grams. A wildlife biologist is interested in investigating whether the mean weight of European grey squirrels is different to the ones found in England. A sample of 50 European grey squirrels are such that the distribution of their weights is still normal with standard deviation 33.3 grams. Find at the 1% level the critical region for the test, stating your hypotheses clearly. So let's explore this. We have that the H0 hypothesis is mu equals 550 and H1 is mu does not equal 550. Notice that the key word is different, and when we have different, this implies a two-tailed test. We're going to let X represent the weight of the grey squirrels in England, and we're going to assume H0. So X is distributed normally with mean 550 and standard deviation 33.3. And therefore we have that X bar is distributed normally with mean 550 and variance 33.3 squared divided by 50. And therefore X bar is distributed normally with mean 550 and variance 4.70933 squared. In this example, this is the shaded region which is called the critical region. 550 is the mean. Since we're testing at the 1% level and we're conducting a two-tailed test, we're going to have to divide 1% by 2. So we have 0.5% plus 0.5% equals 1%. And if we convert to decimals, we have 0.005 plus 0.005 equals 0.01. And therefore, since we're finding the critical region at the 1% level, each tail has probability 0.005, as we can see from the diagram. Let's now find X bar such that probability of X bar being less than this little X bar equals 0.005. And using our calculator, we can input the mean, the standard deviation, and the probability to find X bar. So the mean is 550, standard deviation is 4.70933, and the probability is 0.005. And this implies that X bar, or the little X bar, equals 537.87. Similarly, we can find X bar such that probability of X bar greater than this little x bar equals 0.005. Or equivalently, probability of x bar being less than x bar, the little one, equals 0.995. And again, using our calculator, we can input the mean, the standard deviation, and the probability to find this little x bar. So the mean is 550, the standard deviation is 4.70933, and the probability is 0.995, giving us from our calculator that x bar equals 562.13. And therefore, our critical region at the 1% level is x bar less than or equal to 537.87 and x bar greater than or equal to 562.13. Now let's take a look at part B. The mean weight of the 50 European grey squirrels is calculated to be 580 grams. Comment on this observation in the light of the critical region. So let's solve this. From part A, we know what the critical region is. The observed value, 580 grams, falls inside the critical region. In particular, it's greater than 562.13. And therefore there is sufficient evidence at the 1% level that the mean weight of European grey squirrels is different to the ones found in England. This brings us to the end of this session. If you have understood its contents, you should be able to carry out hypothesis tests for the mean of a normal distribution and solve real-life problems in context. Thank you very much for listening. To understand this topic in greater depth, do attempt the exercises in your textbook related to this topic.